All right, so we finished up chapter 19 last time, and remember chapter 19, some of the big topics were looking at how carbonyl compounds, specifically aldehydes and ketones, behave under acidic and basic conditions, and reviewing this idea of oxidation and reduction and that kind of the concepts that go with that. In chapter 20, we're going to move into what they call carboxylic acid derivatives, and that's a fair statement. What I kind of like to refer to it as is what do all the other carbonyl groups do? So we'll start with discussing about carboxylic acids, and then we'll move into some of the other carbonyl compounds and just looking a little bit at their properties and reactions and all this kind of stuff. But the first point I'm going to make is probably the most important point. Always lead with your biggest guns, as they say, right? So here's our good old buddy, Mr. Carboxylic acid, okay? Nothing too shocking about it, nothing too surprising about it. It's in the name, and yet we tend to forget about it. What is the most important property of a carboxylic acid? It's that it is an acid, right? And acid-base reactions are going to be predominantly the fastest reactions to happen. They tend to be kinetically and, in a lot of cases, thermodynamically favored. So if you have a carboxylic acid, you gotta think and you gotta understand that it is an acid. So if you put a base into there, acid-base chemistry is gonna happen, right? To shut down that acid-base chemistry, you've got to do a lot of shenanigans, basically, is what it is, right? So you really got to pay attention to that. One of these important concepts that we talk to you guys about quite a bit, and then maybe don't emphasize as much, is this idea of keeping in mind what the pKa's are of different hydrogens and functional groups and that kind of stuff. This comes back up quite a bit, especially when you guys get to biochemistry. You guys will be memorizing, have fun with that, by the way. You guys will be memorizing all these, the amino acids, and you're like, oh yes, at this pH, blah, 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 will be protonate and all this. Enjoy, right? I am not a fan of memorization. I'm not being dismissive of it. I'm not saying it's not important. It's just, boy, you tell me to memorize something and, right? But what is important, at least in my opinion, and for the realm of organic chemistry, is to kind of have an idea about pKa's, right? Because I know I've mentioned this before, and it's different because we're doing this online thing, right? Understanding a general idea of the pKa's and pH's and all this kind of stuff of different functional groups is extremely important, because it's going to help you kind of say, well, gee, I've got a base around. Is this a strong enough base to deprotonate that hydrogen, right? Or how close are they? Will it establish some kind of equilibrium and these kind of things, right? So when we're dealing with carboxylic acid, kind of the number you can keep in your back pocket is about 4 to 5. Right? That tends to be where their pKa's are of Mr. Generic, carboxylic acid, right? Of course, we can change that, right? We can change that if we go to a very common reagent that we use. So we have our buddy Trifluoroacetic Acid. This has a pKa of about 0 to -1, if I'm remembering. I didn't actually look it up, so you guys can. If I'm way off, then somebody will post it in the comments or something like that, right? But the normal, or the approximate pKa for a carboxylic acid is about 4. As we add a bunch of fluoros on there, we can really drop that down. Now your question might be, who cares? Well, here's the thing, right? Here's the thing. One thing that we kind of avoid is, if this has a pKa of 0, why not just use one of our strong acids, right? HCl or HBr or that kind of thing. Well, something that we kind of black box or wash over or don't, or just kind of wave our hands at is this idea of solubility, right? HCl only comes as a solution, well, in general, only comes as a solution in aqueous, as an aqueous solution. We can buy things like HCl dissolved into ether and things like that, and that's fine. But the idea is, if we want a strong acid and we want to put it into solution, it has to be soluble in that solution. And with trifluoroacetic acid, it tends to be soluble in pretty much any organic solvent that you want, right? So you don't have to worry about getting some kind of HCl dissolved into ether and it bubbles away and you have to keep it cold because you lose it, right? You can do that and it works, right? But, you know, or you could just put a couple of drops of trifluoroacetic acid in there and it's soluble and you don't have to worry about it. You go on with life, right? So solubility and playing with solubilities is one of these important concepts that come up if you're in the lab, but guess what? You guys aren't in the lab, all right? So who cares, right? Okay, so anyway, back to the point before I started meandering there. Keep in mind that carboxylic acids are acids, right? Okay, so how do we make carboxylic acids? Well, we've learned a couple ways already, right? If we take, let me draw that a little bit better. If we take an alkyne and we subject that to ozonolysis conditions, right? So ozone and then our DMS, our dimethyl sulfide, right? We're going to snip, right? We snip the alkyne, we slide it apart, and we fill in the appropriate number of bonds to oxygen, right? So if we cut, right? If we cut 3 carbon-carbon bonds, we better put 3 bonds to an oxygen, right? Or we better make 3 oxygen bonds, I should say. And I'm not talking about a triple bond, right? We have 1, 2, 3 bonds to oxygen, right? So we cut 3 carbon bonds, we make 1, 2, 3 bonds to an oxygen, right? So we end up generating a carboxylic acid functional group. In fact, we end up generating 2 of them, right? Because we snip, we slide, and we slap them right in there, right? That's fine. We can do this. The problem is we have to generate an alkyne. Not too easy to do. We also have to cut carbon-carbon bonds, so we lose carbons along the way, this kind of stuff. But this is a valid method of doing it. We can just do a simple oxidation. We've learned a couple of different ways, but starting with a primary alcohol, right? We have to start with a primary alcohol. Why? Right? Well, all carboxylic acids are terminal, right? They're going to be at the end of the chains that they're part of, right? You can't have an internal carboxylic acid, right? We would call that an ester then, so to speak, right? Which is why we consider it a derivative of carboxylic acid, but we're getting a little bit ahead of ourselves. If we put some kind of oxidizing conditions here, so typically some kind of strong oxidizing metal, sodium dichromate and sulfuric acid and water, right? Whoops, not that quite yet, H2SO4 and then water, right? Which is equivalent to H2CrO4. You might see it written either way there, right? Transition metal, lots of oxygens, indicative of oxidation, right? We can even take permanganate, potassium permanganate, and heat it up, and that will oxidize this also into a carboxylic acid. That's a very common qualitative test, actually, to look for primary alcohols. There's a lab that tends to get done where it's just qualitative functional group testing. So we give you guys an unknown and we say, do these reactions. If we see a precipitant form from manganese, then we know when there's a primary carboxylic acid or an alkene in there and all this kind of stuff. So I'm kind of referring to one of those. I don't know what labs you guys are kind of walking through this summer though, but maybe you guys have seen that done. But anyway, so looking for a transition metal with lots of oxygens, indicative of a oxidation, and that's going to take a primary alcohol into the carboxylic acid. What's good about this, right, is that we don't lose any carbons, right? We don't have to cut anything. What's bad is this is not selective, right? It's going to oxidize amines, it's going to oxidize alkenes and alkynes and all this kind of stuff, right? So these conditions are not selective at all, right? And we've got sulfuric acid around, so if you have alcohols that are not primary, you might eliminate and do all this, right? So really not selective conditions, but hey, it's a way of doing it, right? So we learned about that. This semester specifically, right, we learned about if we can generate an alkylated benzene and we put it under these same conditions, right? Or again, we can come in with permanganate even and heat this up, right? We will end up cleaving any secondary or primary alkyls and just we chew them off and we end up with a carboxylic acid, right? So we end up cutting things again, right? And we end up just leaving a carboxylic acid in its place, right? So pretty harsh conditions to make carboxylic acids, right? But if you think about it, a carboxylic acid is about as oxidized as a carbon can get, right? We could take it to its extreme and make CO2 where we have 4 bonds between carbon and oxygen, but a carboxylic acid, we already have 3, right? So we can't, it's hard to get more oxidized than a carboxylic acid, right? And that's kind of the idea why we have to have these kind of harsh conditions in there, right? But let's see if we can come up with a somewhat milder way of doing this, or maybe a somewhat more preferable way of doing this. So here's a little practice for you guys, or at least a thought exercise, right? Can you guys start from a benzene ring and make this from it, right? Shouldn't be too bad, right? You know, we have to add a bromine, we have to add some carbon, this kind of stuff along the way. So see what you guys can come up with, right? But if we have a primary alkyl halide and we put in some sodium cyanide, okay, under whatever solvent, you know, we probably want to pick, you know, DMSO or something like this, you know, most likely, right? What we'll end up doing is an SN2 reaction, right? And we end up swapping that sodium cyanide in place, right? In place for the bromide there. Don't forget to count your carbons when you do this, okay? If you're bringing in CN, right, we have an extra carbon that's brought in with this process also, right? So we end up generating a nitrile, right? A cyano group. That's usually the 2 common terminologies for those functional groups, right? So we have that, and if we take this, and under relatively mild conditions, let me do this. I kind of work myself out of room here, so duplicate. If we put this under aqueous acidic conditions and kind of give it a little bit of a umph, right, a little bit of heat, right? So whenever you see that delta right triangle, that kind of means heat. What we will end up doing is turning that into a carboxylic acid, okay? Can you guys figure out the mechanism for this? Look at what we have, right? We're under acidic conditions. We have a carbon that has pi bonds to a more electronegative atom. This is just like a carbonyl. Carbonyl chemistry and cyanochemistry share a lot of similarities, right? So we're under acidic conditions. What were some of the steps that happened for carbonyls, ketones, and aldehydes under acidic conditions? What's usually the first thing that happens? How's it going to be different here? So see if you guys can work through the mechanism for this, okay? If not, I think I already did. Through the magic of recording this well in advance, I will have posted some links for you guys that walk through some of this idea with nitrile chemistry there, okay? But see if you guys can come up with it. I promise you have all the tools to do it, okay? You just have to actually pause this video and go, well, gee, I know he really asked me to do this, but you know, this isn't going to be graded, so I'll do it later. Now, okay, you know, I'm not going to come twist your arm, right? All right, so anyway, setting up a condition to do an SN2 reaction, right? And then under relatively mild acidic conditions, we can generate a carboxylic acid. Not too bad, right? The problem being we have to add a sodium cyanide, so we do have to add an additional carbon in there also, right? So we have to keep that in mind also. Don't forget to count how many carbons you have. All right, so we can take a different tactic here then, okay? This should be a very easy question for you guys. How can I do this? Right, well, that's just a simple halogenation. Okay. And then if I take that and I add in some magnesium, okay, I set up a Grignard, okay? So we end up with a Grignard, right? This is stuff we covered in a previous video also where we talked about blocking groups and what are some of the tricks that we can do with halogens. But there we go. There's a Grignard. What do we know about Grignards? They're powerful bases, okay? They're powerful bases. So if we take and we add some carbon dioxide, which is cheap, right? Cheap and easy to get, right? Some carbon dioxide, and we can bubble that through our Grignard, right? And then we come in with an acid workup, why, right? Well, hang on to that thought, or see if you guys can come up with an answer. Right? If we do that, we will end up, right? We will end up making a carboxylic acid where our Grignard was. Okay? Why? Right? See if you guys can come up with a mechanism for that, right? It's a very straightforward mechanism too, right? Draw out the Lewis structure for CO2, okay? There's the Lewis structure for CO2. Aha! This is just a carbonyl, right? It's a C with a double bond to an O. We are under strong basic conditions. How do attacks happen with carbonyls under strongly basic conditions, right? So when I ask you guys to go through these mechanisms, because you guys have seen this before, it's good practice, it's a good thought exercise, right? You may not have exactly seen this before, but you guys certainly have dealt with ketones and aldehydes at this point and how they react under basic conditions, right? So that's kind of the point that I'm making. So anyway, we have a couple of new ways there of generating carboxylic acids, right? With either Grignards or nitrile groups, right? And that's fine. That's something good to keep in mind, right? Let's kind of go in the opposite direction here. So if we have a generic carboxylic acid and we drop the nuclear bomb on it, right? And the nuclear bomb for reduction is LAH, lithium aluminum hydride. This stuff just reduces the crap out of everything. Nitriles even, right? Nitriles and nitros and aldehydes and ketones and carboxylic acids, and we'll learn about anhydrides and acyl halides and pretty much any carbonyl this thing's going to go after, right? LAH is a powerful base and a powerful nucleophile too, okay? And that first part is the most important. It is a base. This is an acid. So what's the first thing that's going to happen when you mix these two together? Well, the first thing that's going to happen is you're going to do an acid-base reaction, right? So just for simplicity's sake, let's do this in green, right? So LAH, right, is essentially just a bunch of hydrides. I'm simplifying it, of course, right? You can take a look in the book and they draw it out, the structure in there, but this is a hydride, right? This is lithium aluminum hydride. We have 4 of those in there, right? So this H minus is going to react with that acidic hydrogen first. Let me draw that in there for completion's sake, right? So the first thing that happens is because we have an acid and a base, we are going to be doing acid-base chemistry, and we end up with then a carboxyl 8. Right? So if you see a deprotonated carboxylic acid, right, you make a carboxyl 8. The saying that I always give my general chemistry students when we learn about naming acids, right, because we learn about this actually in Gen Chem, is the 8-ix, right? If you end with 8, you come from an ic. If you end with ite, you come from an us, right? So a carboxyl 8 comes from a carboxylic acid, right? So just like but anyway, that's not too important at this point, right? Naming, whatever, right? But if I say carboxyl 8, that's what I'm talking about, right? A deprotonated carboxylic acid, right? So that's the first thing that happens. And this is actually, these are actually really darn stable negative charges, right? You can form equivalent resonance structures with them. This is what's present in soap, right? At least not the more modern soaps, those tend to be sulfate based. But if you've ever made soap from oils, right, then you end up doing basically acid-base chemistry, right? You add lye in with some fat and you cook it up, right? And essentially what you're ending up doing is generating carboxyl 8s from the fatty acids that are in there, right? Fatty acids, right, are basically just long-chain carboxylic acids, right? But anyway, so you end up doing this, and then you end up going through and doing the reduction here, right? But what happens, right? What happens next is that something kind of odd happens. And let me see what would be the best way to draw this here for you guys. We'll do, let's see, I'll draw it at an angle here. So we have an aluminum. We have an aluminum right? And we have, oh my goodness, a hydrogen here, right? What happens next is kind of this, right? The aluminum binds to the carbonyl oxygen there while another hydride attacks the carbonyl carbon, right? So we kind of have this situation going on there, okay? You guys with me on this? I don't care too much about the specifics of this reaction. And I'll explain why this has to be in just a minute, or it should be self-explanatory in just a minute. I should really say, okay? Okay, so if we go through the shenanigans here, let's see if we can draw what's happening. So we have, see, blue here and red to a green aluminum. We have the other oxygen down here with the negative charge on it. And we have, let's see, in red to a green hydrogen here, right? Oops, that's aluminum there, right? We basically plopped a hydrogen here at the carbonyl carbon, makes sense, and that aluminum and oxygen are now bound. And that's going to be important, right? Because what have we essentially done at this point? Essentially what we've done is, this is the opening the door step, right? So we started to talk about this quite a bit in the aldehydes and ketones chapter. When you see attack at the carbonyl carbon, we swing open that pi bond, right? So a strong nucleophile attacks the carbonyl carbon, swings up that pi bond, okay? Whenever we swing up the pi bond, we have to look at whether we can swing it back down, right? We open the door and we close the door. So what's going to happen here is, when we decide to close the door, we have to find a good leaving group, okay? So when we decide to close the door, we have to find a good leaving group. Is hydride a good leaving group? No. Is O- by itself a good leaving group? Is this going to be a good leaving group? Heck no, right? Because that's going to kick off an O2-. I can't think of a single instance where we ever see an O- act as a leaving group. But here we have oxygen bound to an aluminum, and this aluminum does have other stuff to it, right? I'm not that good an artist, and I don't want to clutter things up, right? So it's not a naked aluminum atom there, right? So oxygen bound to aluminum, is that a good leaving group? Actually, yeah, right? Oxygen and aluminum are great, great, great buddies. But you guys already knew this, right? Aluminum has a passive surface on it of the oxide, right? Every metal rusts, right? The difference is, when we have something like iron, like when you form iron oxide rust, what we think of, right? It's just flaky, and so it flakes off and exposes more iron underneath it, which oxidizes, which rusts, and then it continues to flake. But with things like aluminum, when it forms its rust, when it oxidizes, it just passivates the surface, right? It doesn't flake off, you just have a thin layer of aluminum oxide on the surface. So it actually prevents some of the reactivity, because aluminum is actually pretty darn reactive, right? We'll leave it at that. But anyway, so this is actually a good leaving group, because oxygen and aluminum like each other quite a bit, right? They're pretty good friends, and so now we can close the door, okay, and kick off a decent leaving group. So let's go down here. This is in red to green. And then we have one blue to our oxygen there, right? So you guys with me? This oxygen is this one here, and we kicked that stuff off. Now what functional group do we have present? Well, now we've got an aldehyde present. The thing is what, right? With LAH, right, we always have an excess of that around. We can't just say, oh great, yeah, I wanted to stop at the aldehyde, so that's it. No, okay? LAH is going to come in, and it's going to react with that aldehyde and reduce it. So LAH, we're probably going to have to heat this up, right? But a little bit. But when you do LAH with a carboxylic acid, you're going to reduce it all the way down into the primary alcohol, okay? So this aldehyde then gets reduced in the next step all the way down to an alcohol. Can you guys do the mechanism for this? You better, okay? So bring in some more LAH, get it all the way down to an alcohol here, okay? So that's kind of useful, right? Because we can take an alcohol and oxidize it back into a carboxylic acid, right? We've learned, or we at least know one method of doing that, okay? But the problem is, as with always, the selectivity of LAH is non-existent, right? It's just going to go after everything. So we do have something that we can do. Let's say that we've got this guy here. Well, if I can draw, okay? So if we, let's say, wanted to make this, can you guys make this starting from benzene? Ooh, it's kind of a tough one, isn't it? You guys can do it though, right? So start with benzene, see if you guys can make this compound here. You guys have it in your tool belt, okay? Anyway, let's say I just wanted to reduce my carboxylic acid. If I threw in LAH, I would reduce both the ketone and the carboxylic acid in this case. But fortunately, we can use something that might look a little bit familiar. BH3 and THF, right? Okay. And this is actually going to be really darn selective towards carboxylic acids. Where have we seen BH3 and THF before? Well, this is our hydroboration, right? So when you guys go back and take a look at one of the most important reactions that you guys learned in the first semester, hydroboration, oxidation, right? We're using that same stuff there, BH3. Again, BH3 is one of these common reagents that we tend to see in pretty much every organic synthesis lab, right? It's so useful in many different places, right? But if we have a carboxylic acid, we can actually selectively reduce that down over ketones to the alcohols, right? So our product here would be aldehydes just kind of hanging out, and we now have a alcohol there, okay? Super useful, okay? Question. Can you guys figure another method of doing this? It'll take you 3 steps, okay? Can you guys think of another method without using BH3 to do this? It'll take you guys about 3 steps to do. When I say it'll take you guys 3 steps, if you come up with a method that takes 5 steps, I'm not saying you're wrong. I'm just, I can think of a way of doing it in 3. The beauty of organic chemistry, when I ask you guys to do these multi-synthesis type problems, is that, it's your guys' chance to kind of let your creativity come out, right? I am just one person who has an idea about how to do these things. But when I say, can you guys come up with another method of doing that, you guys have the tools to do it. Just, I've basically given you guys a box of Legos, right? Saying, I want you to build this from this. And so you guys have your different Lego blocks and you put them together in a meaningful way to construct what I want from you guys, right? Doesn't mean that everybody has to have the exact same way, right? Some ways might be more elegant or simpler than others, but it doesn't mean that they're necessarily more or less correct, right? Okay, I think you guys get the idea. All right, so the last thing that I wanted to kind of introduce is what are some of the other functional groups that we will run into, okay? So we've learned about carboxylic acids, right? We've learned about aldehydes. So aldehyde, ketone, carboxylic acids, okay? One very common functional group that we've already run into quite a bit, an ester, okay? So ester is where we have carbon groups coming off of the oxygen here, right? Not a hydrogen, that would be an ester. So things like polyesters, ethyl acetate, which is the more modern versions of nail polish remover. Those are common examples of esters there, right? So we've seen those in quite a few different places, all right? So amides, we won't talk about amides maybe all too much in this chapter, but we will definitely come back to that. Extremely important. So amides are where we have a nitrogen, and those R's can either be hydrogen or carbons, okay? So this is amides. Well, I guess I should I should write this stuff down for you guys. Ester, amide. Amide's extremely important biochemically, right? Your peptide chains, they call them peptide bonds in biochemistry. That's because biochemists, I guess they want to be cooler than the rest of us and not call it an amide, right? There it is, right? They're just amides. And so you guys will see those quite a bit if you guys are moving on to biochemistry there, right? You'll see them as solvents. Dimethylformamide, DMF, is an amide. That is a very common solvent that we see in the laboratory. Very common in pharmaceuticals, amides and esters and carboxylic acids also, actually, all of these things. Let's see, what else? Oh, yeah. That looks like an ether, right? But if we put two carbonyls, right, this is an anhydride, okay? This is an anhydride. And the reason, or actually I don't know the true origin of it. Whoa. A little bit of zooming in there, pardon me about that. But an anhydride is basically the condensation of two carboxylic acids. If you bring two carboxylic acids together, you can form an anhydride from it, is what it is, right? And you kick off water as you're doing this, right? So if you think about this real quick, do a mind exercise with me, right? You have an OH and an OH, and you end up with one O, right? So you kick off H2 and one of the O's, right? So H2O, right? So anhydride, right? So anhydrides are pretty common as starting materials for reactions. They're used to add protecting groups to a lot of functional groups. Amines and alcohols react with anhydrides quite a bit. Acetic anhydride, a very common protecting group that we can use to add things. They can start polymerization stuff with them also, right? So we got all that. Oh yeah, and everyone's favorite from this chapter. And we will use these guys quite a bit. So, and its buddy, which we don't use as much, but is just as valid, right? So these are acyl halides. So either acyl chloride or acyl bromide. Now, the reason why these are so important is because what we're going to learn is there's an order of reactivity. Okay, there's an order of reactivity. Acyl halides and anhydrides are extremely reactive. Why would that be, right? Well, you guys already know the answer. Okay? You guys already know the answer. In fact, I've already told you the answer in one of the previous videos. You did? I don't remember. Well, this is a good time to say, well, why would those be more reactive than something like an amide or an ester? It's a very good question, very important question. But anyway, what we're going to do is play this game where I want to convert a carboxylic acid into an amide. To do it directly in one step, we can, but we have to do some shenanigans along the way, right? It's not that easy to do. But if we start with an acyl halide to make an amide, it is almost instantaneous. We literally just mix an amine into there and it kind of, it spits out this nice white solid that we can separate and we make our amide along the way, right? Same thing with an anhydride, very easy to do. So easy to react these to go to some of the more, let's call them stable carbonyl groups, okay? But not as easy once you get to the bottom of our order of reactivity. And you're like, okay, stop, so I'm looking at page 910, right? So page 910 on the left-hand side, they give you guys an order of the ranking of the reactivity for your carbonyl groups. So very important to kind of pay attention to that, okay? Because we can use that to our advantage in terms of selectivity, okay? Carboxylic acids, or let's just go with esters or amides, right? They're not as reactive as acyl halides. So we can react the acyl halide first, and kind of the amide is just going to kind of sit there and not do anything for us, right? So there's certain advantages that we can do to this, okay? Or that we can use this to our advantage is really what I meant to say, okay? So there's that. I think this is a good time to kind of pause this. I think oh my goodness, I think this turned into like a 30-minute plus video here already. So here's a good introduction for what we're going to go into next. Next time we're going to come in and we're going to start to explain why these are reactive, and then we're going to start to do some chemistry with those. Okay, so I will see you guys in just a little bit.